Good morning. I'll take my mask off so you can hear me better. I'm Dr. Bill Stewart, and we're going to be doing some math today, looking at some very interesting problems that you encounter in your everyday life. So we're going to start with the notion of a pile of books. So over here are some books that I've read recently during the pandemic, during the summer, and I chose 10 of them. You can see they're different types, different sizes. And the issue that I'm going to deal with right now is, let's suppose you had those on a shelf and you were going to organize them into some type of display. And you realize you could intersperse these books different ways. You know, put this one on the bottom, whatever. And the question is, how many different ways could you do that? And we're talking about 10 books. We're not talking about a whole library. Probably somewhere in your house you have some bookshelf that has 10 or more objects just like this. Okay? So how many different ways? So let's think about that a second. If you think about 10 slots on a bookshelf that are now empty, and you're going to choose books to put in those slots from this pile, okay? Then for the first slot, you will decide to pick one of the 10 as your first book. So what I'm going to do is put these slots right up here. So those are the 10 slots representing the books that are going to be arranged on your shelf. So with an empty shelf and a pile of books, I have to choose to pick one. It could be one from the top, could be one from the middle, could be one from the bottom. In all, I have 10 choices. I can pick any of the 10. Now once I've selected that initial book and placed it in this slot, I look at the pile and I say, how many books are remaining? And it looks like there are 9. So I can pick any of those remaining 9. Once I've put that second book into its slot, I then have 8, and then I have 7, and then I have 6, and then I have 5, and then I have 4, 3, 2, and my last book, there's only one there, so I have one choice. Okay? So now I have an array of numbers representing the choices that I had as I went through this assignment of arranging books on the shelf. So what do I do with those numbers? Well, for every book that I selected here, I have 9 options for the second. For every book I selected here, I have 8 options for the third. So if you think about that, it expands as you walk down through your assignment list. So what we're going to do to get the total number is we're going to multiply each of these numbers together. Because for every choice, you have that many paths you can go for your next one. And that, multiplied together, equals the total number of different arrangements of those 10 books on your shelf. So if we multiply these all together, we will get 3,628,800. Now, we have a mathematical symbol for multiplying numbers together, which start out at some specific number and decrement down by 1 all the way down to 1. And that is called factorial. And a factorial is symbolized by an exclamation point. Okay? So if I wanted to represent this multiplication process, I would say that that is 10 factorial, which equals 3,628,800 books. Or not 800 books, 800 different arrangements of those books. Now that seems like a big number, 3.6 million. Let's think about this for a second. Let's suppose you were asked to arrange those books in every one of those unique arrangements. And you were going to be paid for that. That was your job. And your job basically would be pick one of the unique arrangements, take a picture of it on your smartphone, put it in your memory, so you'd have evidence that every one that you did was different from the others. Someone say, well, I think that's the same as that. No, it isn't. That fifth book and the sixth book are interchanged. Oh, I see that now. I can see the two pictures. So your job is to do that, just for these 10 books. Okay? You're going to do it. Takes 3,628,800 pictures. Now let's just make a few assumptions. Let's suppose you can do an arrangement in 15 seconds. So, you know, they're right in front of you. You just sort of shuffle them around, take the picture, and move on to the next one. So let's say 15 seconds per photo. Okay? So that would give us 4 per minute. So 4 per minute. Now there's 60 minutes in an hour, so that would give us 4 times 60, or 240 per hour. And let's say you're working an 8-hour shift, an 8-hour per day shift. So I've got my calculator here to make sure I don't make any stupid mistakes. So we'll take 8 times 240 per hour. So guess what? You could do 1,920 per day. Okay? So 1,920 per day, we have this many to do. So we'll take 3,628,800. We'll divide it by the number that we can do each of our 8-hour days, 1,920. Let's see what we get. So we'll take 3,628,800 divided by 1,920, which is 1,890 work days. Okay? Now let's say that you don't work 7 days a week. You're a normal 5 day a week person, 8 hours a day, typical work shift. Okay? So we have this many days. Okay? We're going to have 5 days per week. So we'll divide that by 5. And that gives us 378 weeks. So let's say that typical year, let's work, let's not take any time off. Let's not take time off for holidays or time off for a 2-week vacation. Let's just work 52 weeks a year. We want to get this job done. So 52 weeks in a given year. So let's divide that by 52. And guess what? We come up with 7.27 years. All right? So let's just suppose that when you go to college, one of your professors says, you know, I need someone to do some mathematical experimenting with me. I want to take a pile of 10 books. I want to get all the different ways it can be done. I want to take pictures of it all. I want to catalog it so we'll always have it forever. So I can use it in my class. You say, well, okay, I'll do that. Let's see. You'd be there for 4 years, not quite done. Okay, you apply for your master's program. All right, so we'll go get our master's for a year. 5 years have gone by. Still working on the project. So what else can you do if you got to finish this project? Let's apply for a doctorate. So you get in a doctoral program, which is typically 2 to 3 years beyond the master's. So guess what? This project of arranging those 10 books in different ways and taking a picture of them, working at 15 seconds per example, you would have your PhD or be ready to do your thesis in a PhD by the time you would finish this project. So this shows us how quickly simple problems, 10 books on a shelf, how hard is that, can explode into the numbers that make a task like that almost insurmountable and obviously very costly if you wanted to actually do a project like that. Okay, now let's suppose you had a little different problem. You've got 10 books and you want to arrange, you only have room for 3 of them, okay? So we're going to put 3 slots in there, and you want to know, well, how many different ways can I put those 10 books in, taking 3 and arranging them in an order of 10, or of 3 in a row. So let's think through that. This first slot, I have all the books there, so I have 10 choices for the first. Once I pick that one, I have 9 left, and once I pick that second book, I have 8 left. So I've filled 3 slots, and the number of ways I can fill those 3 slots is just multiplying those together. 9 times 8 is 72 times 10, so that would be equal to 720 ways. Much easier job. 720 different ways versus 3 million. Okay? Now let's suppose that you're going to select 3 books out of those that pile as your summer reading. Okay? And you just want to get those 3 books, put them on your end table where you read, and you'll go through them this summer. 3 books. It could be any of those 3. Okay? But order doesn't matter. In this case, the specific book, where it fit in those slots, mattered. Okay? But if order doesn't matter, then what we can do is just say, how do we pick out of those 10 books 3, and we don't worry about the order? Well, we're still picking out 3, but when you look at 3 things, how many different ways can those 3 things be arranged? Well, they can be arranged 3 times 2 times 1, or 6 different ways. If you have 3 things and think about arranging those 3 things in different order, there are 6 different ways to arrange those same books in ways that are different. Okay? So let's look at how we would approach that from a formula point of view. All right? And we're going to define a few terms. So the first term I'm going to define is called permutation. And the thing to remember in permutation is order matters. Okay? And the symbol we use for that is P for permutation. Then we put a little subscript over here, n things taken R at a time. Permutation of n things, in this case 10 books, taken 10 at a time in our first example, okay, and taken 3 at a time in our second example. So the permutation of n things taken R at a time is given by the formula of n factorial, that's what we had up here, n factorial, divided by n minus R factorial. Let's see how that worked down here. We had 10 books, okay? So we have 10 factorial. We are taking them n minus 3 at a time. 10 minus 3 is 7, divided by 7 factorial. Let's look what happens. 10 factorial is 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 7 factorial is 7, 6, 5, 4, 3, 2, 1. The 7 factorial cancels out the bottom part of the 10 factorial, and we are left with 10 times 9 times 8, which is exactly what we had here. Okay? Now, what if we're taking them 10 at a time? Okay? It would be, because that's what we did in the first case, took them all at the same time, one whole big bookshelf. Then n minus 10 is 0, and by design, 0 factorial is defined as 1. So if that's the case, if I take in the first case where we took 10 at a time, I'd have 10 factorial divided by 0 factorial, which is 1, and I just get the 10 factorial that we had in the beginning. That is when order counts. So you can take any number of objects, decide how you're going to put those in spaces, like books on a shelf, and this formula, P of n taken r at a time, is n factorial. Just take the first one, put it on the top, n factorial, divided by n minus r factorial. Now, what if order doesn't matter? We showed you an example here with books where you pick out 3 books, but you could arrange them any way you want it, and they would be the same. And we said for 3 books, there would be 6 different ways of doing that. Okay? So the second term I want to define for you is called combination. And order does not matter. It is given by the symbol C of n things taken r at a time. So that's similar in format to P and R. This is C and R. And C says order doesn't matter. So when we do that formula, it's very similar to the permutation formula. It's n factorial over n minus r factorial. But now we have to reduce the number because order doesn't matter to us. So therefore, we divide it by r factorial. Okay? By r factorial. So now let's look at our example that we had before of the picking from 10, picking 3, order doesn't matter. So that'd be the combination of 10 books, taken 3 at a time, order doesn't matter. The 10 factorial on the top, divided by 10 minus 3, which would be 7 factorial. That's the same as we did before. But now we have to put in 3 factorial. Then the 10 factorial, the bottom part of that is canceled out by the 7 factorial. So remaining on the top, we have 10 times 9 times 8. And on the bottom, we have 3 factorial, which is 3 times 2 times 1. Let me just write that out like that. Now let's cancel some things out. This will cancel that and make that a 3. This will cancel that and make that a 4. 3 times 4 is 120. 3 times 4 is 12. Times 10 is 120. 120 ways. Notice 720 was the way where order mattered. Divide that by 6, you get the 120 that we have here. Now I'm going to erase the board, and we're going to come back and do a problem using the concept of combinations in finding the number of diagonals in a polygon. Okay, so we now have a clean board, and we're going to look at an octagon, 8-sided figure. Regular polygon, all the sides are equal. It's like our standard stop sign that you see throughout the Zanesville area. And a question that might be posed is how many diagonals can you draw in a figure like this? Now what is a diagonal? Well, a diagonal is some line that connects one vertex to another vertex that bypasses an intermediary or several intermediary vertices. So in figures like this, you have sides, which are the outline of the figure, and diagonals then connect all the points that you are not connected by the sides. So the question is, how many diagonals can you connect? So we can use the concept of combinations to solve that problem. So I'm going to write that formula up here again. The combination of n things taken r at a time. So let's see what's going on with this octagon. We have 8 vertices. And a vertex is just a connection of 2 sides. That's a vertex, vertex being plural. We have 8 sides. Let's count them. Let's count the vertices. Start here. 1, 2, 3, 4, 5, 6, 7, 8. Let's count the sides. Start here. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's what we have for an octagon. And so what we're going to do is ask ourselves, how many different ways can you connect 2 points in an octagon that are different? Okay? So, from here to there is a side, from here to there is a side, from here to there is a diagonal. So let's ask ourselves, how many different ways can we connect 8 points, 2 at a time? Those connections will either be sides or they'll be diagonals. That makes sense? Okay, so let's do that. So we want the combination of 8 things, points, connected 2 at a time. Okay, that'll be the total. And then we need to subtract out from that the sides because those aren't diagonals. Well, we know how many sides there are going to be. Okay, there are going to be 8 sides, just like there were 8 points connected. So we're going to subtract 8 from that answer. Okay, so let's now do the combination formula, which is 8 factorial divided by 8 minus 2, 6 factorial, times 2 factorial minus 8. Okay? So remember that the 6 factorial cancels out the bottom part of the 8 factorial. So what we have, 8 times 7, 6, 5, 4, 3, 2, 1 gets canceled out. 2 times 1 is 2. So 8 times 7 is 56. Divided by 2 is 28. So this is going to be minus 8. So this is going to be 28 minus 8 is 20 diagonals. Okay? Now let's up the numbers a little bit. I mean, I suppose you could have taken a couple minutes to draw in all the diagonals and then count them all up. There'd be 20 of them in there. You might think, well, where would they all be? Well, there's all different ways those things connect. Now, why did we use combination and not permutation? Because a connection doesn't matter if it's from this point to that point or that point to this point. They're the same line. They're the same side. They're the same diagonal. So order of picking the points does not matter. That's why combination works in this type of problem. So let's say we have a 100-sided figure. Now I challenge you to draw in all the diagonals for a 100-sided figure. But you might be asked that on a test. Let's see what that would look like. So, combination of 100 vertices, points, taken again 2 at a time, remembering that will give us the total number of connections. We then have to subtract the 100 sides to make sure we focus on the resulting diagonals. So let's do this. We have 100 factorial divided by 100 minus 2 is 98 factorial. And then we have the 2 factorial again. Okay? Now, if you have a calculator, and it's a scientific calculator, you could put in 100 factorial and see what number you get. It basically blows up your calculator. Not physically blows up, but gets way bigger than you can display. But we can calculate it by getting rid of a major portion of the 100 factorial. So 100 times 99, then we have 98, all those get canceled out by that, and then we have our little 2 here. And then we want to make sure we subtract the 100 from the sides. So 100 times 99 is 9900 divided by 2 minus 100. And it goes to about 4, and that carries 1, so that goes about 8. That goes about 9. And then 5. I think that's right. Let me just double check that in our math before we get too far down the road. 99 divided by 2, 4950. Let's subtract the 100. And so the total number of diagonals in a 100-sided figure would be 4850. It'd be a lot of drawing if you were asked to do that, but the calculation is very simple. Now you might say, that's an interesting application for polygons, but what's so interesting in my everyday life? Well, we all in today's world are connected through all kinds of technology. Now think about it. If I'm going to send a Facebook post to my friend, that's a connection. Some technology, some server, some network has to allow that unique connection to take place. Take all your friends, all the friends of everybody else's friends, and all that, and ask yourself how many connections are floating around in our world today just in terms of social media, emails, and those kinds of things. Enormous, enormous, enormous number. And yet engineers have to design and build systems that will take care of all those connections so that you can have that type of communication. As a big task that was sort of taken over in the last 30 years, developing that kind of network, we take it for granted nowadays, but behind the scenes there's an infrastructure that's very exciting and a very big field in which people can productively earn a living. Okay, so I'm going to erase this, and when we come back we're going to look at having lunch at a Subway restaurant. And the question I'll pose is, how many different sandwiches could you walk out of a Subway with that would be different from anybody else? So I'll erase the board and be right back with you. Okay, so we're back with near lunchtime, so we're starting to think of sandwiches, and we're going to go to Subway today and ask ourselves, how many different ways can I have a Subway sandwich made for me, for my particular desire, made my way. Okay, so I've put out here's a foot long, and we realize that many of us don't eat a foot long, but we actually divide it in half right across there. Okay, so what I've done, when you go into a Subway, and I eat at Subway quite often, is you are asked to direct the server in the creation of your sandwich. And there's a certain logical order in which you can communicate that to the server, and if you do it in the right way, it makes it much more efficient. So the first thing is, what size? Is it going to be a foot long, or is it going to be a 6-inch? So there are two options for the size of the sandwich. The type, like turkey and ham, Subway Club, roast chicken, all that. Well, if you go onto the website for Subway, there are 19 different sandwiches that they list. Now that doesn't mean every Subway, like the one at Maysville Avenue or the one up on Maple or at Walmart, doesn't mean that they will all have each one of those sandwiches, because they tailor it to the demand in the community. So they try to fine tune that so they don't have so much. We're talking about how numbers explode. Well, Subway's got to deal with that also. Okay? But there are 19 that they have developed for use in their store networks. Now, they brought something on several years ago, which means they could toast the sandwich for you. So you could either toast it or not toast it. So there are two options there in terms of whether it goes into the toaster oven, in or out. Okay, what about cheeses? They list 5 cheeses: cheddar, American, pepper jack, whatever. My favorite's American, so that's what I get. Now we have choices of breads within all these sandwich types, and they list 9 different breads. Now honey oat is my favorite, but when I travel, there are many Subway establishments that don't offer honey oat. They just offer 9-grain wheat, okay, which is my second option. But there are 9 different breads, okay. Now, with respect to cheeses, there are 5 different kinds of cheeses, but I could ask them not to put it on there. So really, I have the 5 cheeses, but I also have the option of no cheese. So there are actually 6 different things I could tell that person: no cheese or one of the 5. 6 different ways. Of course, with bread, I can't very well have a sandwich without a bread, okay? And so we're good through there. Now we come to veggies. Veggies is a real sort of issue here with Subway sandwiches. So your sandwich is in front of you, and what would you like on it? And they often say lettuce and what else, because almost everyone wants lettuce, okay? Well, in terms of veggies, there are 14 different veggies. Now, how do we handle that? Do we just multiply by 14? I would say no, because basically you have these trays of veggies, and as you scan them, you have a choice to make. If these are tomatoes, I can either have tomatoes or not have tomatoes. So I have 2 different ways the tomato can be answered. Let's talk about lettuce. I can put lettuce on or no lettuce. Okay? So we have this for all 14 different ways. And if they were all zeros, meaning I didn't take any, then I would have no veggies. I say no veggies, plain. But once I start saying what I want, then I get into all these different multiplications. So actually, it is 2, because I have a choice in each box of each container of vegetables, and I have 14 different choices. So it's 2 to the 14. Okay? Now 2 to the 14, so I'm going to actually put this in parentheses because that's not actually correct. I'm going to take 2 and raise it to the 14 power, and I get 16,384. So when you look at the vegetables, you are making decisions on those vegetables that explode this sandwich experience. Just explodes it. These are all nice manageable numbers. Then all of a sudden we get hit with 16,384 ways that you could put vegetables on that. Think about vegetables as a series of lights. Each vegetable container is a light bulb. And if you choose tomatoes, the tomato light bulb goes on. Bing, it lights up. If you don't choose tomatoes, it stays off. This is the binary system on which computers are based. It's either on or it's off. And what we really have in the vegetable portion of the Subway franchise is we have 14 lights, just like computer lights, that we're going to turn on or off, binary system, to allow us to represent the vegetable layout that we want on our sandwich. Okay? Now that brings us to sauces, and there are 16 different sauces that they have developed. Again, not every store has every one of them, but those are available. Now, let's think what we have. To find out the total number, we have to multiply each of these numbers and get a total, okay? And I've done that, and let me just do that real quickly here. So we take 2 times 19 times 2 times 6 times 9 okay, I'll try it again. I messed up on that. 2 times 19 times 2 times 6 times 9 times 16,384 times 16. Big number. Let's see how big that is. There's your thousands. There's your 100,000s. Here's your millions. Guess what? This is billion. So we're talking about 1.075 billion with a B different sandwiches that can walk out of a Subway restaurant. Now, this brings to mind a quote that I remember from the autobiography of Lee Iacocca, who ran Chrysler Motors. When he came to Chrysler, he was trying to find efficiencies to reduce production costs. And when he started to look at all the different options that consumers asked to be put on the various automobiles that Chrysler made, and he started to do the numbers just like we have done with Subway sandwiches, okay? He made the statement that there were more different automobiles that the Chrysler Motor Company could manufacture than there are atoms in the known universe. That's how this factorial thing just blew up in the car manufacturing business. If you go to buy a car now, you'll typically find that the manufacturers have isolated the various options into packages. For example, I drive a Subaru. When I purchased that Subaru, I didn't have to go through a whole lot of, well, do I want this, do I want that? No. Depending on the model you wanted, there were 4 different classifications, from limited to premium to touring to elite. I guess there's a 4th one there. Inside each of those identified packages, all the options are set. If you want limited, here's what you get. If you want touring, this is what you get. You don't have many options. The only thing at the end is you might have to decide whether you want to have a hookup for a trailer, whether you want to have rubber mats, sort of like mats to protect your floors and so forth. And there's maybe 3 or 4 things you would even mention to the salesperson that you might choose for your Subaru. So the world has changed. And the reason the world is changing to try to understand what most consumers want and then to put them in packages is to get away from the Subway experience of having it your way and the ramifications of that when you're trying to prepare to produce that. So I hope you've enjoyed this lesson on counting. This is the mathematical counting. We've talked about permutations, we've talked about combinations, we've talked about diagonals in polygons, and we've talked about setting up a problem to determine how many different ways a very simple everyday experience like having lunch can develop into a horrendous or very large set of possible outcomes. Have a good day.